For more than 100 years, humanity has searched for a clean, powerful, and reliable source of energy that does not poison the planet or run out over time. Coal filled the skies with smoke, oil fueled progress but caused wars and climate change, and even renewable sources like wind and solar struggle with one major weakness. They do not always work when we need them. Nuclear power solved part of the problem by producing massive amounts of electricity, but traditional nuclear power plants rely on splitting atoms, a process called nuclear fission. While fission creates huge energy, it also produces dangerous radioactive waste and carries the fear of accidents that can make entire regions unlivable. Because of these risks, scientists began searching for a better solution, one that copies the process that powers the stars themselves. That solution is nuclear fusion. Fusion works by joining tiny atoms together instead of breaking them apart, releasing enormous energy with almost no long-term waste. For decades, fusion sounded like a perfect dream that was always 30 years away. Many people stopped believing it would ever work. But deep in northern Germany, something quietly changed that story forever. In a research facility far from public attention, German scientists achieved a fusion result that shocked the global scientific community. On May 22, 2025, they managed to hold superheated plasma, hotter than the core of the sun, stable for 43 full seconds. This may not sound impressive to someone outside science, but in the world of fusion research, this moment was historic. Plasma is incredibly unstable. It moves violently, twists, and tries to escape any container that holds it. Keeping control for even a few seconds is extremely difficult. Holding it stable for over 40 seconds at such extreme temperatures proved that a design many scientists had abandoned decades ago might actually be the key to future fusion power. The machine responsible for this breakthrough is called Wendelstein 7X, and is unlike anything else on Earth. Most of the world invested billions of dollars into a different fusion design called a tokamak. Tokamaks are simpler in shape and easier to calculate, which made them attractive for early research. Huge projects like ITER in France and experimental reactors in China and the United States all followed this path. Germany, however, chose a much harder road. Instead of following the crowd, German scientists committed to a machine design called a stellarator, which uses extremely complex magnetic fields to control plasma without relying on electric currents flowing through it. At the time, many experts believed this approach was too complicated, too expensive, and too risky to succeed. Computers were not powerful enough. Calculations took years, and even a tiny mistake in design could ruin the entire machine. Because of this, most countries abandoned stellarators completely. Germany did not. The decision to continue working on stellarators was not driven by pride or stubbornness, but by a deep understanding of fusion's biggest weakness. Tokamaks rely on strong electric currents inside the plasma itself to stay stable. Those currents make the plasma unpredictable and prone to violent disruptions. When a disruption happens, the plasma crashes into the walls of the reactor, forcing the system to shut down. This means tokamaks often operate in short bursts rather than continuous operation. A real power plant, however, cannot turn on and off every few minutes. Cities need steady electricity day and night. Stellarators avoid this problem by creating all the magnetic control externally. This makes them far more stable in theory, but incredibly difficult to build in practice. For decades, stellarators remain an idea that looked good on paper but failed in real experiments. That changed with Wendelstein 7X. What makes this achievement even more remarkable is that Wendelstein 7X is not a power plant. It does not produce electricity for homes or factories. Its purpose is to prove that stable, long-lasting fusion plasma is possible. By reaching temperatures over 20 million degrees Celsius and maintaining stability for 43 seconds, the machine showed that stellarators can compete with and possibly surpass tokamaks. This success did not happen overnight. It took more than 60 years of theory, 19 years of construction, and the combined effort of scientists and engineers from across the world. Yet this single experiment changed how experts think about fusion energy. It suggested that humanity may finally have a realistic path toward clean, safe, and nearly unlimited power. For the first time in history, fusion no longer feels like a distant dream. Instead, it feels like a difficult but reachable goal. Germany's fusion machine did not solve the world's energy problem in one day, but it proved something equally important. The right idea, even if ignored for decades, can still change the future. And this is only the beginning of the story to understand why Wendelstein 7X is so important. It helps to understand what this machine actually is and why it looks so strange compared to other scientific devices. At first glance, Wendelstein 7X does not look like a power machine at all. It looks more like a giant metallic sculpture from a science fiction movie. Twisted steel pipes, curved shapes, and looping structures surround a central chamber, creating a design that seems almost chaotic. But every curve, every bend, and every angle exists for one reason: to control plasma, the most difficult substance humans have ever tried to manage. Plasma is often called the fourth state of matter. It is not solid, liquid, or gas. Instead, it is a cloud of charged particles moving at incredible speeds, reacting violently to heat and magnetic fields. When heated to millions of degrees, plasma cannot touch any physical surface, because it would instantly destroy it. This is why fusion machines must suspend plasma in empty space using magnetic forces alone. Wendelstein 7X uses a design called a stellarator, which controls plasma using only external magnetic fields. Unlike tokamaks, which rely partly on electric currents flowing inside the plasma, stellarators shape magnetic fields entirely through their external magnets. This difference may sound small, but it changes everything. Electric currents inside plasma are unstable by nature. They twist, break, and collapse without warning, causing disruptions that shut down the fusion reaction. Stellarators avoid this problem by removing internal plasma currents altogether. Instead, they use carefully designed magnetic fields that twist around the plasma in 3 dimensions, holding it steady like invisible hands. This approach creates far greater stability, which is essential for continuous operation. The challenge is that these magnetic fields are extremely difficult to design and even harder to build. The heart of Wendelstein 7X consists of 50 massive superconducting magnets, each one shaped differently from the others. These magnets are not simple loops or circles. They twist and curve in precise ways that must match computer calculations down to the millimeter. If even one magnet is slightly out of place, the entire magnetic field becomes distorted and the plasma will escape. This level of precision was nearly impossible when stellarators were first proposed in the 1950s and 1960s. At that time, scientists lacked both the computing power to calculate such complex magnetic shapes and the manufacturing tools to build them accurately. This is one reason why many countries gave up on stellarators and focused on simpler tokamak designs. Germany, however, waited patiently for technology to catch up with theory. Another astonishing feature of Wendelstein 7X is the extreme temperature difference inside the machine. The superconducting magnets operate at around minus 270 degrees Celsius, just a few degrees above absolute zero. At this temperature, electrical resistance disappears, allowing powerful magnetic fields to flow without energy loss. Just a few meters away, inside the central chamber, the plasma reaches temperatures above 20 million degrees Celsius, hotter than the core of the sun. Within a single machine, humans have created both the coldest and hottest environments ever produced on Earth. Keeping these extremes separated while maintaining precise magnetic control is an engineering achievement unlike anything before it. Fueling the plasma inside Wendelstein 7X is also a delicate process. Scientists inject tiny pellets of frozen hydrogen into the chamber at high speeds. These pellets are only a few millimeters in size, but they play a critical role. As they enter the plasma, they evaporate and feed the fusion reaction, maintaining the correct density and temperature. Too much fuel cools the plasma and shuts the reaction down. Too little fuel makes the plasma unstable. Every injection must be perfectly timed and adjusted in real time based on how the plasma behaves. Powerful microwave systems heat the plasma further, pushing it closer to the conditions needed for fusion. All of this must happen while the plasma floats freely inside magnetic fields, never touching the reactor walls. What makes Wendelstein 7X truly special is not just its appearance or complexity, but what it proves. For decades, critics claimed stellarators were too complicated to work in real life. Wendelstein 7X showed that with modern computers, precision manufacturing, and international cooperation, stellarators are not only possible but highly effective. By maintaining stable plasma for long periods, the machine demonstrated a level of control that fusion researchers had hoped for but rarely achieved. This success changed how scientists around the world think about fusion design. The strange shape of Wendelstein 7X is no longer seen as a weakness. Instead, it is now seen as a sign that stability, not simplicity, may be the true key to future fusion-powered. TO understand why Germany's success with Wendelstein 7X is so surprising. We need to look back at the history of fusion research and the critical decisions scientists faced more than 60 years ago. In the early days of fusion science, researchers around the world believed that copying the process that powers the sun was only a matter of time and effort. By the 1950s and 1960s, several experimental machines had already been built, but none could hold plasma long enough or hot enough to produce useful energy. At this crossroads, two main designs emerged as serious candidates for controlling fusion plasma: the tokamak and the stellarator. Both designs aimed to trap plasma in a donut-shaped chamber using magnetic fields, but they used very different methods to achieve this goal. The choice between these two paths would shape the future of fusion research for decades. Tokamaks quickly gained popularity because they were easy to design and understand with the technology available at the time. Their magnetic fields were more symmetrical, which made calculations simpler and construction faster. Tokamaks use powerful external magnets, but they also rely on an electric current flowing to the plasma itself. This current helps twist the magnetic field, keeping the plasma confined. In early experiments, tokamaks showed better performance than stellarators, reaching higher temperatures and stronger confinement. Because of these early successes, countries like the Soviet Union, the United States, and later China and Europe invested heavily in tokamak research. Over time, tokamaks became the global standard for fusion experiments, attracting most of the funding, talent, and attention. Stellarators, on the other hand, followed a much more complicated path. Instead of using electric currents inside the plasma, stellarators rely entirely on external magnets to create twisted magnetic fields. This means every magnetic coil must be carefully shaped and positioned to guide the plasma along a stable path. In theory, this approach offered a major advantage: much greater stability. Without strong currents inside the plasma, stellarators are far less likely to suffer from sudden disruptions that cause the plasma to crash into the reactor walls. However, this advantage came at a heavy price. Designing stellarator magnets required extremely complex mathematical calculations that were beyond the capabilities of early computers. Even small errors in design could lead to complete failure. Manufacturing such complex shapes with high precision was also extremely difficult and expensive. As a result, early stellarator experiments produced disappointing results, reinforcing belief that the design was impractical. By the 1980s, most countries had given up on stellarators entirely. Funding dried up, research teams disbanded, and the idea slowly faded from mainstream fusion research. Tokamaks, despite their known problems with instability, continued to improve thanks to better materials, stronger magnets, and more advanced control systems. Large international projects were planned around tokamak designs, including ITER, which became the most expensive fusion experiment in history. Many scientists believe that even if tokamaks had limitations, they were the fastest and most realistic path to commercial fusion power. Stellarators were seen as an interesting but ultimately failed experiment. Germany, however, took a different view. German fusion researchers closely studied the weaknesses of tokamaks and concluded that their biggest flaw was also their greatest risk. The same plasma current that made tokamaks easier to build also made them unstable. These instabilities, called disruptions, can release enormous energy in a fraction of a second, damaging reactor walls and forcing shutdowns. In a laboratory, this is an inconvenience. In a power plant, it would be unacceptable. Electricity systems require constant, reliable output, not short bursts followed by resets. German scientists believed that if fusion was ever going to power cities and industries, stability had to come first. This belief led Germany to continue investing in stellarator research even when it seemed unfashionable and risky. Instead of chasing short-term performance records, they focused on long-term reliability and continuous operation. Advances in computing during the 1990s and 2000s gave them new tools to revisit stellarator designs with much greater accuracy. Powerful supercomputers can now simulate complex magnetic fields in 3 dimensions, allowing researchers to optimize designs before building anything. At the same time, precision manufacturing techniques improved, making it possible to produce the complex magnet-shaped stellarators require. With these tools finally available, Germany committed to building Wendelstein 7X, a machine designed to prove that stellarators could work as intended. This decision was not guaranteed to succeed. It required patience, massive funding, and a willingness to face criticism from the global scientific community. But in the end, Germany's persistence paid off. Wendelstein 7X showed that the stellarator path, once dismissed as a dead end, could lead to stable and powerful fusion plasma. By refusing to abandon a difficult idea, German scientists reminded the world that progress does not always come from following the easiest path. Sometimes it comes from believing in a better solution long enough for technology to catch up. Building Wendelstein 7X was not just a scientific challenge. It was one of the most difficult engineering projects ever attempted in the field of experimental physics. From the very beginning, many experts believed the machine would never work. Not because the theory was wrong, but because the precision required to turn that theory into reality seemed almost impossible. Construction officially began in 2005 at the Max Planck Institute for Plasma Physics in Germany, but planning had started more than a decade earlier. The design was so complex that engineers spent years creating detailed computer models before a single piece of metal was cut. Every component had to be designed to survive extreme conditions, from temperatures colder than outer space to heat hotter than the center of the sun, all within the same machine. AT the heart of Wendelstein 7X are 50 massive superconducting magnets, each weighing several tons, and each shaped differently from the others. These magnets are responsible for creating the twisted magnetic fields that hold the plasma in place. Unlike simple circular coils, these magnets curve and twist in 3 dimensions, following paths that look almost random to the human eye. In reality, their shapes are carefully calculated to guide plasma smoothly around a reactor chamber. The problem is that these calculations allow almost no room for error. If a magnet is misplaced by even 1 millimeter, the magnetic field can become distorted, causing plasma to drift toward the walls and collapse the experiment. Achieving this level of accuracy with such large and heavy components pushed engineering to its absolute limits. To meet these demands, German engineers had to invent entirely new tools and methods. Standard industrial equipment was not precise enough, so custom-built machines and robotic systems were developed specifically for Wendelstein 7X. These robots could position magnets with extreme accuracy, while advanced scanning systems checked every component multiple times before installation. Each magnet was measured, adjusted, removed, and reinstalled repeatedly until it met exact specifications. This process was slow, expensive, and frustrating, but skipping any step would have risked years of work. The assembly alone required more than 1 million hours of labor, involving specialists from many different fields, including physics, engineering, materials science, and cryogenics. One of the most remarkable challenges was managing temperature extremes. The superconducting magnets must be cooled to about minus 270 degrees Celsius to function properly. At this temperature, electrical resistance disappears, allowing strong magnetic fields to flow without energy loss. To achieve this, the magnets are cooled using liquid helium, one of the coldest substances known. At the same time, the plasma inside the reactor reaches temperatures above 20 million degrees Celsius. Keeping these 2 environments separated requires advanced insulation, vacuum systems, and constant monitoring. Any failure in cooling could damage the magnets, while any failure in plasma control could destroy the inner walls of the reactor. The fact that both systems operate safely within a few meters of each other is a testament to extraordinary engineering skill. Despite careful planning, the project faced serious delays. The original completion date was set for 2006, but problems with the superconducting coils caused repeated setbacks. Some coils did not meet quality standards and had to be redesigned or rebuilt. Others required additional reinforcement to withstand the enormous forces generated during operation. Each delay increased costs and fueled criticism from skeptics who argued that the project was a waste of money. By the time construction was complete, the total cost had reached approximately 1.4 billion euros, and the timeline had stretched to nearly 19 years. Many people believed that even if the machine were finished, it would fail to deliver meaningful results. Finally, on December 10th, 2015, Wendelstein 7X was switched on for the first time. This moment was filled with tension and uncertainty. If the magnetic fields did not match computer predictions, it would mean that years of design work were flawed. To the relief of the entire team, the magnetic field behaved exactly as expected. The plasma followed the intended path, confirming that the complex magnet geometry worked in practice. This success did not mean the mission was complete, but it proved that the most difficult part of the project had succeeded. The machine could create and control plasma as designed. However, creating plasma was only the beginning. The real goal was to hold it stable for long periods at high temperatures. Achieving this would require years of further upgrades, testing, and fine-tuning. Each experiment brought new challenges, forcing scientists to improve heating systems, fueling methods, and plasma control strategies. Wendelstein 7X slowly evolved from a risky engineering experiment into a powerful research platform. What many once called an impossible dream was now a functioning machine, ready to test whether stellarators could truly deliver on their promise. After nearly a decade of testing, upgrades, and careful experimentation, Wendelstein 7X finally reached the moment it was built for. By 2025, the machine had gone through several improvement phases, each one designed to push plasma performance closer to the conditions required for practical fusion energy. Scientists were no longer just trying to prove that the stellarator concept worked. They were now asking a more serious question. Could this machine operate in a way that resembles a real power plant? This meant holding plasma at extremely high temperatures, keeping it stable for long periods, and doing so in a controlled and repeatable way. On May 22nd, 2025, all of these efforts came together in a single experiment that would reshape how the world views fusion research on that day. Researchers managed to sustain plasma inside Wendelstein 7X for 43 continuous seconds at temperatures exceeding 20 million degrees Celsius, with peaks reaching close to 30 million degrees. To put this into perspective, the core of the Sun is estimated to be around 15 million degrees Celsius. While fusion reactors on Earth require higher temperatures due to lower pressure, achieving and maintaining such heat is still an extraordinary challenge. Plasma at these temperatures moves violently and constantly tries to escape magnetic confinement. Holding it stable for even a few seconds requires perfect coordination between magnets, heating systems, and fueling methods. Holding it for over 40 seconds represented a major step forward, especially for a stellarator. A design once thought incapable of such performance. One of the most important measurements achieved during this experiment was something called the triple product. This value combines three key factors that determine how close a fusion system is to producing usable energy: plasma density, temperature, and energy confinement time. In simple terms, the triple product measures how much fusion potential the plasma has. For decades, only tokamak reactors had achieved high triple product values, reinforcing belief that stellarators were inferior. During the 2025 experiment, Wendelstein 7X reached triple product levels previously seen only in tokamaks, and it did so with a plasma volume 3 times smaller. This result shocked many experts and forced a reevaluation of long-held assumptions about fusion design. Fueling played a crucial role in this success. Scientists used a highly advanced pellet injection system that fired tiny pellets of frozen hydrogen into the plasma at precisely controlled intervals. These pellets refueled the plasma without disrupting its stability, a balance that is extremely difficult to achieve. During the record run, approximately 90 pellets were injected over the 43-second period. Each pellet had to be timed perfectly. Too many pellets would cool the plasma, while too few would cause instability. For the first time, operators were able to adjust the fueling rate in real time, responding to changes in plasma behavior as the experiment unfolded. This level of control is essential for any future fusion power plant, where conditions must be adjusted continuously to maintain stable operation. Heating the plasma to such extreme temperatures required powerful microwave systems that delivered energy with remarkable precision. These systems raised ion temperatures to levels twice as hot as the Sun's core, while diagnostic instruments monitored every aspect of plasma behavior. Advanced sensors measure temperature, density, and radiation in real time, allowing scientists to understand exactly how the plasma responded to different conditions. This data was invaluable, not only for confirming the success of the experiment, but also for guiding future improvements. Every second of plasma operation generated a massive amount of information, helping researchers refine their models and predictions. Perhaps the most important outcome of the 2025 breakthrough was what it proved about stability. Unlike tokamaks, which often struggle with sudden disruptions, Wendelstein 7X operated smoothly throughout the entire experiment. There were no violent collapses, no damage to reactor components, and no forced shutdowns. This demonstrated that stellarators could deliver steady, controlled plasma performance over extended periods. For scientists focused on building real power plants, this result was more important than any single temperature record. It showed that fusion energy could one day be produced continuously, rather than in short bursts. The global reaction to the experiment was immediate. Fusion researchers around the world recognized that something fundamental had changed. Stellarators were no longer a side project or a theoretical curiosity. They had proven themselves as a serious contender for the future of fusion energy. While Wendelstein 7X itself will never generate electricity for the grid, its success marked a turning point. It showed that the long, difficult road Germany chose was not a mistake. Instead, it may have been a path that finally brings fusion energy out of the laboratory and into the real world. Although Wendelstein 7X is located in Germany, its success is not the achievement of one nation alone. Fusion research has always required collaboration on a global scale, and the 2025 breakthrough was a result of years of coordinated effort between scientists, engineers, and institutions from many different countries. No single laboratory could develop all the technologies needed to control plasma at such extreme conditions. Each part of the puzzle, from fueling systems to diagnostics and simulations, demanded specialized expertise. The success of Wendelstein 7X showed that fusion energy is not a national competition, but a shared scientific mission with potential to benefit all of humanity. One of the most important contributions came from the United States, where researchers at Oak Ridge National Laboratory developed the advanced pellet injection system used during the record-setting experiment. This system was unlike anything used before in stellarator research. It produced a continuous strand of frozen hydrogen, which was then cut into tiny cylindrical pellets and fired into the plasma at high speeds. These pellets traveled hundreds of meters per second and had to survive long enough to reach the plasma core before evaporating. Designing such a system required deep knowledge of materials science, cryogenics, and plasma physics. Without this precise fueling method, Wendelstein 7X would not have been able to sustain plasma for long periods at high temperature. European partners also played critical roles. Scientists in Spain developed advanced computer simulations that predicted how fuel pellets would behave once inside the plasma. These simulations helped operators adjust fueling strategies and avoid conditions that could destabilize the plasma. Hungarian researchers provided ultra-fast camera systems capable of capturing plasma behavior in real time. These cameras allowed scientists to observe how pellets interacted with plasma, revealing details that could not be seen with traditional sensors. Meanwhile, researchers in Germany and neighboring countries developed powerful microwave heating systems that delivered energy directly to the plasma with high efficiency and precision. These systems were essential for raising plasma temperatures to fusion-relevant levels. American institutions, such as Princeton Plasma Physics Laboratory, contributed advanced diagnostic tools, including X-ray spectrometers that measured ion temperatures inside the plasma. These measurements helped confirm that the plasma was reaching the extreme conditions required for fusion reactions. Other diagnostic systems, developed at the Max Planck Institute and partner universities, measured electron density, radiation levels, and magnetic field behavior. Each instrument provided a piece of the overall picture, allowing scientists to understand how the plasma evolved over time. This constant flow of data was critical for fine-tuning the experiment and ensuring safe, stable operation. What made this collaboration especially effective was a level of coordination between teams. Data collected during experiments was shared quickly across institutions, allowing researchers to analyze results and propose improvements in near real time. Scientists from different countries regularly worked side by side at the Wendelstein 7X facility, bringing diverse perspectives and expertise. This collaborative environment accelerated progress and helped solve problems that no single team could have addressed alone. It also created a shared sense of ownership and purpose, reinforcing the idea that fusion energy belongs to everyone, not just one nation. The success of this international effort also had an important psychological impact on the fusion community. For years, fusion research had been criticized for slow progress and unfulfilled promises. Many people outside the field doubted whether practical fusion energy would ever be achieved. The results from Wendelstein 7X helped restore confidence by showing that decades of investment and cooperation were producing real, measurable progress. It demonstrated that complex scientific challenges can be overcome when nations work together toward a common goal. Perhaps most importantly, the global nature of the success laid the foundation for future fusion development. Building a commercial fusion power plant will require even greater cooperation, involving industry, governments, and research institutions worldwide. The technologies tested at Wendelstein 7X, from fueling systems to control algorithms, will inform designs far beyond Germany. As fusion research moves from experimental machines to demonstration power plants, international collaboration will become even more essential. The story of Wendelstein 7X proves that when humanity faces a challenge as large as global energy supply, cooperation is not just helpful, it is necessary. The success of Wendelstein 7X did more than prove a scientific concept. It sparked a new way of thinking about how fusion energy could move from the laboratory into the real world. For decades, fusion research was almost entirely driven by governments and large public institutions. Projects were slow, extremely expensive, and focused mainly on scientific discovery rather than commercial use. While this approach was necessary in the early stages, it also created a gap between experimental success and practical application. After the 2025 breakthrough in Germany, that gap began to shrink. Scientists who had spent years working on Wendelstein 7X realized that the technology was finally mature enough to imagine a fusion power plant designed from the start for real-world electricity production in 2023. Even before the record-breaking experiment, 3 scientists from the Max Planck Institute for Plasma Physics made a bold and unusual decision. Instead of continuing only within the academic system, they chose to form a private company focused on commercial fusion. Their names were Francesco Sartino, Lucio Milanese, and Jorgen Lyon. Having worked closely with Wendelstein 7X, they understood both its strengths and its limitations. They believed that the lessons learned from the Stellarator could be combined with modern computing and new materials to design a reactor far more efficient than anything built before. This decision led to the creation of Proxima Fusion, the first company to spin out of the Max Planck Institute, with the goal of building a commercial Stellarator power plant. One of the key insights behind Proxima Fusion's approach was the role of modern computing and artificial intelligence. When Wendelstein 7X was designed in the 1990s, even the most powerful supercomputers were limited in their ability to simulate plasma behavior. Engineers had to simplify their design